So the talk is originally called Elegant Builds at Scale with CEO, but latest and greatest, 3.2, I think the release candidate 3 is out. So, and a couple of other features that are just in Gradle Master I'm going to show today. So why do we care about scale? There's a lot of inefficiency and pain out there when it comes to build scalability. And so I want to start with showing you a picture of a typical enterprise build master at work. And in my experience, and I've talked and consulted many organizations over the last years, is that developer productivity is much lower than it could be because of insufficient, inefficient builds and build infrastructure. And as always, it is fascinating how people and teams can get used to pain, right? Even if it costs them dearly, they might say, well, it could be worse. I still can see a little bit, right? And one nostril is not too bad for breathing, actually. While this is already not a good position to be in, right? We want to work with a very efficient build infrastructure, right? The future will give the octopus even more arms. The code bases are growing very fast. Many organizations have growth rates 20%, 50%, 100% per year, right? Even with 20%, it means your code base doubles in the next 4 years. And when you have, let's say, a build performance problem now, it will not get better. And the multitude of new platforms you have to deliver to because of mobile and all the diversification we see when it comes to target platforms. Multi-language is now the norm in enterprise software stacks. And finally, microservices are posing a big challenge from a continuous delivery perspective, right? They add a lot of complexity. So this is the time to invest into your builds, whatever technology you're using, but definitely you have to do something, right? And it is not just about the obvious pain, right? The car industry had no obvious pain in the 90s when it took them 40 plus hours to assemble a car. But when Toyota managed to do it in 20 hours, it became a pain for the other companies. So if you look at LinkedIn, in 2011, there were 1,000 engineers and they released a new version of their software every 30 days, which is not too bad. I would say that is still today above average for that size of a team, right? And that, but if you look at it from a factory perspective, when a feature was finished and ready to go, the feature was by average 15 days in the shelf before it reached their customers and users. So a couple of years later, they brought it down. They're now at 2 releases per day, right? So that means the inventory term for feature to live in the shelf is now 0.25 days. And they get a lot of other advantages. At the same time, their code base was growing. They're now at 2,000 engineers. So my question is, are you there yet, right? Very successful software companies like LinkedIn and Netflix, for example, they invest tremendous amount of resources into build infrastructure to make the developers more productive, to become more productive as an organization. And they do it very successfully. Both, by the way, use Gradle as their foundation. But my point is that organizations that are not able to catch up with such ambitious companies are doomed. Software is eating the world, and the companies that are most successful in efficiently creating software, they will succeed. So regardless of whether you think, oh, our build infrastructure is good or bad, better is better. The competition is getting hotter and hotter, and those organizations going to ever more verticals, right, to compete with traditional companies. Okay, so when we talk about elegant builds at scale, right, what are we talking about? The most obvious thing that comes to our mind is build performance, yes. And obviously performance is a very important scalability factor, but there is much more, right? If extendability is not good, you have a fast build, but it doesn't automate half of the stuff that needs to get automated, right, in your organization. Deeply support developer workflows, and I will show some examples what I mean with that later on. You can have fast build systems that don't capture key aspects of typical developer workflows, like, for example, working on multiple repositories at the same time. I've seen that quite a few times. Build systems have to be easy to configure for developers and to be used by developers. Otherwise, you can have a fast and extendable build system, but when it's extremely painful for developers to work with, then it is also very inefficient, right? And I've seen that a lot of times that the build system exposed a lot of complexity to developers. The build wikis were huge, right? And that is definitely something that is very, very important to me, that aspect. And then build infrastructure must be maintainable, right? Which is not necessarily a trivial thing. And another aspect is monitoring and analytics of your build infrastructure, right? How easy is it for you, let's say you work in a distributed team, right, to see, hey, the team in Bangalore, right, or the team in the US, do they have particular issues that are not visible where I'm working from, right, when they, for example, run their local builds. And finally, the build should help to enforce software health, like separating the API from the implementation. We talk about that, or dealing with the health of your binary dependencies. We will also talk about that later. Okay, so, and I show you a couple of major features in Gradle. Most of them are new that target one or multiple of those dimensions. So let's get started with the performance dimension. And a big part of that is build output caching. So one question, who of you is using Gradle? Okay, so it's about 50-50. That's good. I think everyone will get a lot of stuff out of this. So first of all, what makes a task in Gradle? The unit of build output caching, right, as well as the unit of execution in Gradle is a task, right? In AND, it would be a target. For Maven users, it would be a goal you hook into a life cycle. That would be the unit of work in Maven, right? And Gradle caches the output of every task. We talk about that in a second. There are some other areas where we do caching, for example, external dependencies, but that is not build output, right? So in any case, every Gradle task, right, has inputs and then actions, right, what the task is actually doing, compiling, running the tests, jarring, and they have outputs. And for example, right, an input for the compile task would be the source compatibility setting, right, of the compile task. And of course, your sources. And of course, the class path. The output, obviously, in this case, are the compiled classes. So what is special with Gradle compared to the other Java build systems, right? Inputs and outputs are explicitly modeled in Gradle. Every Gradle task that ships with Gradle has its getters annotated to describe the inputs and outputs, right? And you can do that for your custom tasks, right? When you're extending Gradle. And if a task describes the input and the outputs, whenever you run Gradle, we store the hash of all the inputs and all the outputs of the task, right? So the actual output of this cache is in a build directory, right? But the hashes live somewhere else that fingerprint this output and the inputs. So the build directory is similar to the target directory, right, in Maven. So the build directory is part of this cache. And the way Gradle works is when you run the Gradle build again, it checks, have the inputs changed of the task, have the outputs changed, right? And if not, the task is up to date and the task is not run. If any of the input and output has changed, the task is re-executed and the output is regenerated. So some tasks throw all existing output away and fully rebuild. Others do it incrementally. For example, the Gradle incremental compile task. Gradle provides an API for incremental tasks to do this efficiently, to inform them what has changed. But we're not talking about incremental tasks, right? That is a separate topic. We are talking about a task output cache, right? That is binary. Has something changed? Re-execute the task. If nothing has changed, we don't do anything. Okay. So, and every Gradle user knows about the up-to-date feature, right? It is prominently shown on the command line, right? When a Gradle task was up to date, you can see that. But it is important to understand the details of the current caching mechanism, right? So the cache kicks in for a task when the content is the same the last time the build was run. So for example, when you switch between branches within your project directory, right? You check out the master branch, you check out the feature branch, you build the master branch, then you build the feature branch. If you go back to the master branch, you don't have any up-to-dateness anymore because you've built the feature branch before. The current Gradle cache only stores the output of the last build. Well, there's only one build directory, right? So it is the way we're doing things right now. It's a natural constraint, right? So the other thing is, when you check out the same project twice, let's say in two separate directories, the build output is not shared, right? You have to build the same projects from scratch. It's only within the same project directory that we're doing the caching. Obviously, output between different machines is not shared, right? And, very important, it only works when you don't run a clean build, right? So a clean removes the build directory, and thus the cache content is removed. So a clean build forces everything to be rebuilt. Some people may say, oh, that is why you do a clean build, right? Maven users do that all the time. But we talk about this later. We don't think that should be always necessary. Okay, so I want now to talk about the new task output cache in Gradle. It is not a replacement for the current up-to-date mechanism, which will continue to have its place. It's an additional caching layer or potentially multiple layers. So what is the purpose of that new output cache, right? So first of all, this cache stores the complete history of build output. So for example, when you can, with this cache, you will be able to switch back and forth between branches, and the build results of all the previous build runs are all stored and reusable, right? And it will work per machine, right? So you can have the same project checked out in two directories, and the build results are shared. Most importantly, you will be able to share build results across machines. So this will enable a distributed cache for Gradle build output. And finally, the cache will also be used for clean builds, right? As it stores the content outside of the build directory. So, and that has a lot of very positive effects. So let's talk about how does it work, right? So the first thing we needed to do was to extend the input and output model to make this reliable and efficient, right? So first of all, a task has to opt in. The task implementation has to opt in to be cached in a new output cache. All the tasks shipped with Gradle will opt in, but for your custom task, you have to explicitly tell Gradle, hey, this task should use the new output cache, right? The reason for that is that we want to make sure that you have reflected upon the fact whether your inputs and outputs have been properly defined. For example, the version of the toolchain used by a task should be part of the inputs, right? If you don't want to share the output when one build is using version 1.0, let's say of a source code generator tool, and the other build is using version 2.0, those outputs you don't want to share, right? You only want to share between builds that use the same version of that tool. And when you have implemented a task in a way that it just picks up whatever version there is without making that explicit, right? Then you should not use the new cache for that task. To make the cache efficient, right, because we want to have as many hits as possible, you annotate inputs that do not affect the actual outputs, like the verbose setting, right? It is only relevant for the console output. And then we don't use it for calculating the cache key. And finally, and that is one of the interesting bits here, right now, when Gradle calculates whether inputs or outputs have changed, Gradle uses the absolute paths to hash the file content, right? Or to hash the inputs. And this basically means you will not have cache hits between projects that do not live in the same directory on the same machine, right, usually. And that, of course, is not very exciting, right? So that is why in the extended input and output model, you can tell Gradle which part of the path should be used to calculate the cache key, right? For example, for your source files, it would be probably everything under source main, right, Java. And you can explicitly tell Gradle how to do that. So that is one basic evolution of our caching, that we extended the input and output model to reflect the additional needs of the new task output cache. And how does this work in practice? Well, there are two locations for this task output cache. So one is a shared server. This is called a distributed cache. The CI builds, they read from it and write to this cache, right? And CI builds will deeply benefit from this cache. They usually always do clean builds. So they run different jobs with different user homes against the same project. So the same thing has to be rebuilt over and over and over. And so with the new cache, that should dramatically speed up CI build times. Developer builds, they usually only read from the distributed cache. That reduces the latency and is important for reliability. Right? So, and the other cache instance, optionally, is on your machine to reuse output when you switch between branches, for example. Okay, so what are the pieces that are required so that you can use the new cache? So I talked about the extended input-output model that is part of Gradle 3.2, which is available now, and we will do some improvements, some additional fixes in Gradle 3.3. The Gradle Java tasks, they're already configured to opt into the new cache. There's a REST API and a Java adapter to connect to any cache backend you want to provide for the distributed cache. We need to provide an authentication API. At the moment, when you have access to the cache backend, you have access to it, right? There's no authentication happening right now. A configuration DSL where you can configure which builds should only read, which builds should read and write. There's already a cache backend reference implementation that you can use for a distributed cache. And Gradle will ship with a built-in local task output cache with version 3.3 or 3.4. So to wrap this up, we have a public performance enterprise large test project that we use for performance optimizations, right? And when you run that with a distributed cache or without a distributed cache, right, the effect is dramatic, pretty spectacular, right? 300 seconds versus a couple of seconds, and the overhead the distributed cache or the cache in general is introducing is really tiny. So it's very much looking forward that all of you, at least that are using Gradle, start using a distributed cache. Okay, so now we talk about the next dimension, another feature I'm super excited about, how a build system can really support in a deep way typical developer workflows. So, and this feature I want to show is called composite builds. So what does it mean, composite builds? Composite builds is about combining independent Gradle builds and binary, and when you combine them, binary dependencies they have between each others are replaced with project dependencies that are built from source. So let's look at an example. So what we have here is a Java project. It's a Java application. It applies the Gradle Java application plugin, which gives you a run task and tasks to bundle the application. In any case, this project, my app, here's the main class name. The application plugin needs to know that, and here's the main class of my app. And this project has two binary dependencies on a number utils library as well as a string utils library. And when we look into the main class, you can see how it's used, right? The string util library is used to concatenate some strings, and the numbers library is used to add two numbers, 15 and 10. Okay, so when we run this app now, see, oh, the answer is 26. So there's a bug somewhere. So, okay, let's go back to our code. Let's jump into the add method, and we see, oh, the +1 shouldn't be there, but hold on. This is decompiled from the binaries in IntelliJ. We can't change the code here, right? So what we have to do is we have to go to the myutils project, have to find the class, that implements the add method. And then we see, okay, here's the bug. Let's remove the +1. Okay, let's do that. And okay, let's rerun the build. And still not fixed. Why is it not fixed? I need to republish, right? Okay, what a pain in the neck. And imagine you do this, you have some more complicated refactorings, you do this all the time, right? You forgot to publish, you wonder why is it not working. It's not a good workflow, right? So, okay, let's see what we can do with Gradle. With Gradle, we can say, okay, include another build and combine it with the current build. And when you run this, what you can see now is that we have not used the binary dependencies, but have built myutils from source. And you see the answer is 25, right? So, there are more refactorings I want to do. So I would like to do that conveniently in the IDE and not in two different IDE windows, right? And two different IDE instances. I want to do that in one project. So I tell Gradle to generate the IDE metadata and inject the myutils build, telling Gradle, hey, combine those two builds, right? And after I've done that, you see I have now myutils and my app both in the IDE. They have source dependencies between each other. So I can now go into the main method of my app, can say, okay, I want to have a minus method, right? And can use all the goodness in IntelliJ to create this minus method. And okay, that's right. So let's see if that works. Here we go. The answer is 5. So nice. And one way to do composite builds is to do it via the command line. Another way is to do it in the settings.gradle. So I can persist that behavior in my app, at least for a certain period of time, that I say, hey, include build myutils. And then I can just go on the command line and don't need to inject it there, but can just run the build, and the answer is 5. Okay, so just to be sure, if we remove this, right, and run the build again, this will not work because now we're using the stale binary dependencies and they don't know about a minus method. Okay, finally, what I can also do, and that's I can create completely synthetic composite projects, right? So, and in this composite project, I have a settings.gradle where I define all the builds that I want to combine, right? Number of microservices that have a separate repository, for example, and you see there are no sources in that project, nothing, right? Just the settings.gradle and a build.gradle, and I can just say Gradle run, and then it combines those two builds into one, and I can import them into the IDE. So that is the composite build feature. And I think the reality is with microservice architecture that the number of repositories will increase. So I think it's a very important capability to make working with multiple repositories very convenient. And so for quick local experimentation, cross-repository refactoring, as we have seen, right? And a typical scenario is when you have a big monolith, right? And you want to now break this down into smaller repositories. This is a wonderful thing, right? This feature. And imagine to do this together with the distributed cache, how fluent that will be, right? When you have, let's say, a big monolith that takes 20 minutes to build, right? You start your day in the morning, right? CI has filled the distributed cache, and you can start with the refactoring right away. Okay, another nice use case is when you write Gradle plugins, standalone Gradle plugins, you can with composite builds, you can now easily combine them with a test project to try them out instead of always publishing them and then consuming them in a test project. Okay, next feature I want to talk about. One of my favorite topics. It addresses many scalability dimensions at one. Enforce your API with Gradle. Let's look at the following project. So this is a multi-module build. It could be in Maven or in Gradle, right? It has 3 modules that you build from source, right? Core, that depends on utils, and utils on some lib. And they also have external dependencies, right? And so my question is now, when you compile a core, right, with Maven or the way Gradle currently works, right, what is in your compile class path? Everything, exactly, yes. So the whole transitive graph. And is that a good idea? You need it? You need all the dependencies to compile? Yeah, so, and that's the interesting question, right? So first of all, you pay a price for that, right? From an API perspective, the build system assumes, for example, that the utils API consists of all the classes of util as well as all the classes of sumlib plus all classes of commons lang and all classes of commons IO, right? Big API. And so in general, I think this behavior is evil, right? It creates, as I said, a vast surface area of your API, often 2 orders of magnitude for bigger builds, larger than necessary, right? They're hard to debug and reason about because of the size and the implicitness that often comes with it. It introduces fragility, right? If you depend on some of the dependencies in a transitive path that is deeply nested, right? And then you remove the parent dependencies, out of a sudden, you're wondering, why is my code no longer compiling? The vast surface areas leads to many, many unnecessary compiles, especially in larger projects where this hurts the most. Okay, so why not using the direct dependencies and nothing else, right, for the compile class path? In fact, the very first spike I did many years ago for Gradle had a non-transitive compile class path, but for reasons we will discuss soon, it was not quite that easy to solve that problem, and I had to revert to transitive as a temporary solution. I thought for just a short time, but anyhow, finally we have addressed the issue. And the short story is, the new normal with Gradle will be that the compile class path is non-transitive by default, right? The new behavior will be opt-in, so existing builds will continue to behave the same way. So how does this work with Gradle? Let's look at a demo. Okay, so here we have the projects already showed in the graph, right? We have core, sumlib, and utils, and let's go to the IDE, and you can see in the core project we have the dependency on commons collections, and we have a project dependency, so source dependency on utils. In utils we have a dependency on sumlib, and a dependency on commons lang. And in sumlib, we have a dependency on commons IO. Okay, so and if we now look at this is now using the new mechanism, right, where compile dependencies are internal, right? So in utils, the compile dependencies that utils declared, or anyone else, any other project declares, are internal. They are not exported, if you like, right? So, okay, let's try this out. So first we compile the utils project, right? And I have enabled some debugging statement. So utils depend on sumlib, and we can see the compile class path. The compile class path includes the sumlib.jar. So in a new, this new set of features also includes multi-JDK support. That's why you have to compile Java 8 name in the name of the library. But anyhow, it's some libjar, it's commons lang, but it does not include the commons IO dependency of sumlib, right? So only the direct dependencies of my utils and everything worked fine. Okay, so let's compile core. And here we get an exception, right? So the compile failed. The compiler says, hey, there is a class. Okay, first let's look at the compile class path. There's the utils jar and the commons collection jar. And in the main method of the core project, we refer to a class that the compiler cannot find. Okay, so let's go into the source code. Let's go to the main class, and we see here is this function class that we're referring to. Actually, it's an interface, right? And okay, and this interface is defined in the sumlib project, which is a dependency on utils, but not a dependency on core. Okay, so what do we do, right? How do we solve that? What do you think? Yeah, so we could declare it. We could declare a first-level dependency in core, right? That would work, but I don't think it's the right solution, right? So we could do that, compile, blah blah blah. Because the reason why I don't think it's the right solution is the following. If you look why we use this function class, right? The string utils method, which is part of the utils project, right, is requiring an implementation of an instance of function to be passed to the method, right? So it's part of the API of the utils project, right? In core, I only use function to use the utils project, right? And you can see, right, it's part of the signature of the encode method. So what we should do, right, and what you can now do in Gradle, you can say, you can declare another dependency as part of the API, right? Boom. And then this dependency is basically will be exposed when you have a dependency on utils, right? So, and if you do that, you can see everything is working fine now. And we have in the class path for compiling core, right, we have utils, we have commons collection, and we have sumlib. Yeah, but not commons IO and all the other stuff. Okay, so the recommended default for Gradle will be non-transitive, but as shown, you can tell Gradle easily that additional libraries need to be exported and are part of the API. And this solves one part of a bigger problem, right? So can we further reduce the surface areas, right? So when core depends on utils and sumlib, it does not depend on all classes of those modules, right? There are internal packages it should not require, right? Wouldn't it be nice if we could Gradle tell somehow about that fact, right? So let's look at the next demo. So so the utils project has an internal package, and there is a string internal kind of helper method in there, which capitalizes a string, uppercase a string. So, and in the core project, I think, that could be useful, right? I can use that for a nice printout in uppercase. So, so I create an instance of string internal, and have now a super nice uppercase printout of Devox. Okay, so let's compile this. Right here we have string internal, let's compile this, and let's remove the clean. I only run a clean build so that I triggered the compile so that you could see the debug output, what was the class path. Usually I don't run clean builds. Okay, and what you can see, the compile was successful, right? I could easily use the string internals class. Obviously, it should work because, hey, utils is part of my class path and it contains the string internal class. Okay, but the utils team is pissed off. All the people that use the internal classes, right? They want to protect them because they want to be able to refactor them without paying attention to backwards compatibility. So they can't wait to get the latest version of Gradle to do the following. They can now declare which packages should be exposed. So they say, com acme util is fine, but not com acme utils internal. And if you compile this now, you will get a nice exception. Yeah, the compile failed, and because the string internal class is not visible, it's not part of the compile class path of core. And I think this is very, very important. Big API surface areas, big API surface area is expensive, right? And the larger it is, the more expensive it is. And that is true whether you provide an API to other teams in your organization or to the world. It doesn't matter, right? They impose massive refactoring constraints, right? If the whole organization uses all your internal methods, well, good luck with refactoring this code base, right? And still have friends after that. And they require, if you do a good job, they require expensive testing for backwards compatibility. You must not break those, right? And that is even harder if this is not part of one build, but if the consumer and the producer of the API are decoupled, right? And the consumers use different versions of your API, right? Then things become really complicated the bigger the surface area is. And this can bring your development speed to a crawl, right? Talk to the JDA folks, right? How hard it was to make the JDK modular after the fact, right? Those are the best engineers on the planet, and it took them years to get modularity introduced, right? Talk to us, right? Gradle, we have 2.5 million downloads per month, right? We have millions of users, and we are in a very conservative domain. We have to guarantee backwards compatibility, but at the same time, we want to continue to innovate, right? Reducing the surface area is key, right? So you could ask now, is that an exotic opinion that I have here, how important that is? Well, I would say not quite, because this concept is at the heart of Java 9, right? So, and that is another thing I want to talk about. So Gradle makes it now extremely easy to enforce APIs, right? And Gradle paves your way to Jigsaw, right? So in multiple ways. So first of all, you can start right now to enforce your APIs, whether using Java 6, Java 7, or 8. You can, with Gradle, enforce your API at build time with all the benefits we discussed. Initially, we recommend just to model how the APIs are used currently to prevent further degeneration, right? Enforce the current usage, but not further outreach into other internal packages. And then you can improve from there, right? And the other thing, how Gradle, and that is a key thing, right? Modeling your API and your implementation, that is what Jigsaw is about. So you can start doing this now with Gradle, get all the benefits, and when you're ready for Java 9 and Jigsaw, well, then you're definitely ready to use the Jigsaw features because you have already defined that in Gradle. So another thing that will help you is it is easy to migrate with Gradle's multi-JDK support. I will talk about that in a second. And finally, Gradle creates Jigsaw module info and multi-release jars, all that out of the box for you. So I don't have time for a full demo, how this works. I just want to give you some idea how this looks like. So with Gradle, you will now be able to define target platforms, right? And when you say, hey, I want to try out my build with Java 9, the only thing you need to do, you need to add Java 9 to the target platforms. It's the only thing you need to do. Everything else Gradle does for you. It creates all the tasks automatically to compile with Java 9, right? And all the wirings between the sub-projects. So that is super easy to configure for developers, although it is a pretty complex problem that we need to solve, dealing with all those different jars for different Java versions, but Gradle does that for you. And then when you add Java 9 as a platform, we know, oh, Java 9 means Jigsaw, so we created the module info automatically for you, just for the Java 9 jars. The multi-release jar that is part of Jigsaw will be built for you. So it couldn't be more convenient. Imagine you would need to do that with Maven profiles. Just little joke. The other thing you're able to do, which is, I think, even better than multi-release jars, is that you can specify dependencies per Java version, right? You can specify dependencies that are used across Java versions, but then you can say, hey, the Java 7 version of my jar uses commons.io 2.1, and Java 8 uses 2.5 because there might be some closures in there, right? So very, very powerful. Okay, so the other thing I want to mention is compile avoidance. Gradle offers you compile avoidance when a transitive dependency changes, when any code changes into internal classes, and when any change happens in the implementation of API classes. So I want to give you a quick demo on that. So I'm running Gradle core compile Java just to show you everything is up to date, right? And now I go to the utils project, right? And remember, core depends on utils, and I change the version of commons lang, right? And when I recompile core compile Java 8, it is still up to date. Utils, I needed to recompile because the class path has changed. But because this is no longer leaking, right, I don't need to recompile core. So another interesting thing is, here's the string internal method, right, that is not exported. So I refactor this, I just changed the name. So I basically changed the public signature of one of the classes in util, but core is still up to date because, hey, the internal classes are not exported, so they don't trigger a recompile of core, right? So we'll talk later about what this API jar is about. So the next thing I want to show you, and that might surprise you, so now we're touching the string utils class, and that is exported to the core project. But what we're doing is we're just changing the implementation of the encode method, right? We're just extracting a variable here. So we don't change the public signature, and even that doesn't trigger a recompile. And that is why we built this API jar. So the way Gradle works is that for every jar that is consumed, it creates an API jar that is basically only contains the skeleton of all the public methods and their arguments, nothing else, right? And so when you change the implementation of a method, the API jar will not change, and that is basically used to indicate, right? And that is part of the compile class path of compile of the core project. So when you change the implementation of a class that isn't your class path, it will still not trigger a recompile. So, oops, that was not good. Sorry, I wanted to show you something else. Let me see. Fast forward. I screwed up. Give me a second. Been there. No. Okay, so, okay, doesn't matter. I just wanted to show you how it actually kicks in when you change the public API. So the previous demo has shown you in detail how the compile avoidance works, but it didn't give you a feeling for the performance effect, right? So let's look at a more realistically sized, kind of medium-sized project with 190,000 lines of code, right? So 19 sub-projects, and they have dependencies between each other, right? Pretty clean dependency graph. In reality, it's often much more messy, right? And so when everything is up to date, the compile is very fast, right? A second or so. Now let's change, and this is how Gradle works currently, or how you would do it with Maven. Let's change the version in project 1 of any of the dependencies, and because this is leaking, right, the old way that things are working, you need to compile everything, because the class path is leaking. It triggers a recompile of all those projects that depends on project 1, directly or indirectly. And oops. Now, second. So sorry, my goodness. In dual screen mode, I don't have a control for the recorded demo, and the fast forward is for some reason not working for me. So let's do it one more time. Sorry for that. Oh, so much more to show. So this is taking now change of the compile class path, triggers all those recompiles, and you could argue, well, at the end of the day, it's only 11 seconds, right? But it's so much nicer if it's only 1 second, right? And for larger projects, that can be 5 minutes, 10 minutes, 20 minutes, right? When you do some heavy annotation processing and stuff like that. So the way it should be working is, and it will be working with the latest features of Gradle, right, is that you, when you change the compile class path in project 1, right, only project 1 gets recompiled, the rest is not affected, and you have the feedback in 1 second. And that is much more fun to work with. Okay, so some of you might have heard that Gradle is now also offering Kotlin as a language that you can use to describe your build. Who is aware of that? Yeah. Who knows about Kotlin? That's interesting. Only 20%. Okay. So it's a new JVM language provided by the folks from JetBrains, the creators of IntelliJ. Statically typed, wonderful language for the JVM. Right. It's used a lot in the Android world for writing Android apps, but it's now used more and more in the Java world. Netflix is a heavy user, right? So I live now in the Bay Area. Many companies there are picking it up. It's, it comes with all the, let's say, discrete credentials of JetBrains, and it's also very, very nice for DSLs, right? And we embraced Kotlin as an alternative to Groovy, right, to scale better when it comes to ease of use for developers because of IDE support, and maintainability by the build masters because of navigation within the build logic, and for performance reasons. So 1.0 of the Kotlin DSL will be ready by the end of the year, fully statically typed, outstanding IDE support. It's one of the problems with Gradle currently, that you don't have good IDE support when you write build.gradle scripts. I guess everyone agrees to that, right? No content assist, no strong statically type checking, no navigation, no good support for build class paths. So all of that is changing. It's high performing because it's statically typed and compiled, right? It's also very well suited for developing Gradle plugins. I want to give you a quick demo. So here we have a Hello World application, right? And I want to quickly create a build script with Gradle that builds this application, right? And I can now use full content assist. I can say apply, application plugin, and hey, I have quick documentation lookup. I can say, oh, what do I do with this application plugin, right? And I see, I need to configure the application plugin convention object. So boom, say configure, application plugin convention, right? And main class name, that's the property name. So full content assist, right? And can also configure the Java plugin, right? And again, don't need to look up the DSL reference. Finally, right? I have everything at my fingertips, right? And repositories, content assist for the whole DSL, right? Big progress. Something, one of the biggest wishes of our users to have better IDE support. And let's see if that actually works. Let's try to build this thing. So Gradle, let's run. Hey, so it actually works. You can describe your Gradle build in Kotlin, and you can execute it, right? You can run it. So the other thing, you can navigate now into the Gradle source code, right? So, right, that is completely new. It's not. It's very hard to achieve today, right? You basically have to have the Gradle source code checked out to do that, right? And again, the whole DSL, including builder patterns, are supported. So when you want to do a copy task, let's say, right, all supported. And there's one other thing that is very cool. So when you want to use an external plugin and you define that in your build script section, right? After you click save, this dependency, in this case a Nebula plugin, is downloaded in the background and automatically added to your build script class path, and you have content assist for that, right? So after you do that, right, you specify the URL and the plugin, you can see that there is now the resolution rules plugin, right? That is now available in the content assist. Okay, good. So and we're still making the DSL nicer. So this is how it will look like probably when we have reached 1.0, right? So, but it's not dynamic. It's all statically typed, full content assist, and the same look and feel than you have for the Groovy DSL, just with all the additional goodness you get. Okay, so don't have much time left. I want to talk about some dependency management capabilities that are available in Gradle as part of the bigger Gradle plugin ecosystem. So one thing are resolution rules. Very powerful declarative rules for Gradle dependency management, right? So you can define resolution rules with Gradle in a centralized JSON file, and you can share this information across all the teams in your organization. And I think this is a missing piece for keeping in control of your dependency graph, right? So you apply the Nebula resolution rules plugin, and there are some default resolution rules, right, that ships with the resolution rules plugin, and you just treat that as a dependency, right? That is downloaded from your repository, and you can add your own resolution rules, right? And can also add them to the resolution rules configuration, and then they are downloaded and automatically applied to all the builds in the organization, right? And you can define resolution rules for replacing dependencies. So you can define a company-wide rule. Whenever Google Collections and Guava is used at the same time, kick out Google Collections because it's superseded by Guava, right? You can substitute. You can say whenever log4j, but the replace rule means when Guava is not in the class path, then use Google Collection, right? The substitute rules means whenever you find log4j, for example, replace it with slf4j over log4j, right? You can specify minimum version rules. You can specify deny rules that when this dependency or this version of a dependency shows up, let the build fail, right? You can have reject rules that basically are used when you do dynamic dependency management. You can specify a rejected dependency explicitly, but when you use snapshot, right, they will never used as the latest dependency, the ones that are rejected. You can specify exclude rules. You can specify align rules that you say for a certain set of dependencies, let's say from Apache Jersey, right, they have multiple dependencies that belong together. They should all use the same version, right? Very, very powerful. And this is how you define such rules, right? You can say align, group example foo, and that means now all the dependencies of example foo that have that group ID will use the same version. By default, it's the highest version. You can specify other versions if you want, right? This is how a replace rule looks like, right? Google Collections replaced with Google Guava. You can specify a reason and other interesting metadata. Very, very powerful. The other thing I want to show is dependency locking. Who of you is using Maven snapshot dependencies of the Maven users? So they have their downsides, let's put it like that, right? And with dependency locking, right, you can use dynamic dependency. You can say, always give me the latest, but you can lock a certain state of your dependencies down. So for example, at Netflix, what the developers do, they use dynamic dependencies to always get the latest, but they only trigger that in the morning, and then they use the dependency lock plugin to tell Gradle, hey, create a log file with exactly the versions I have retrieved right now, and I want to use them for the rest of the day, right? Because I don't want to get interrupted by continuous updates of dependencies. You can use, if you use dynamic dependencies, right, you can create a stable state to roll back to. You can commit log files for reproducible release builds. So even if you use dynamic dependencies, right, you can check in the log file into version control when you take a release, and that build will be forever reproducible with exactly that dependencies that have to be resolved when you did the release builds. So you have, when you apply the log plugin, you have generate log, update log, save log, commit log. The other thing, another interesting dimension, right, is build script health and build script maintainability. And there is a wonderful Gradle Lint plugin available, right, that maintains the health of your build script. It issues warnings, it can fail, it can warn, it can even fix things that are not okay with the build script to make it very easy for the developer. So examples are duplicate classes are used in the class path, unused dependencies, an old Gradle wrapper version. And you as a build master can configure whether the lint plugin should warn and should fail. And when the developers get a warning or failure, they can run Gradle lint fix, and lint goes into the build script source code and fixes the actual problem. Very powerful. You can create your own rules, right? So you have, with Gradle, you have very strong control, right? How the build scripts are evolved by the developers, right? Because often people say with Gradle you have so much freedom. Well, you have also freedom to be very strict. Finally, I want to quickly mention another important part of build scalability, Gradle Cloud Services and build scans, right? This is a service that collects and connects all your build data in a centralized service. So whenever you run a build, right, CI or local, the build metadata, right, which tasks were executed, which dependencies were used, which tests were run, how long did it take, what was the memory situation, they're all collected and sent to this service, right? So you can use that to efficiently collaborate on build problems. You can use it to analyze, to continuously optimize feedback cycles of your build and quality of service. You can collect your own custom values. It's deeply integrated with Gradle. Learn more about that at gradle.com or come to our booth for a demo. Yeah, I hope I could show you what a powerful build platform Gradle is, right? So if you're not using it yet, have a thorough look, right? A lot of innovation is happening. I think Gradle has the potential, even if you're using it with the new features, or if you're not using it and think about migrating to it, it has the potential to significantly and positively impact your organization. Thank you very much.